Good morning. Today we start with Lemming. We continue with mini course on non-construct technologies and applications.
Thank you. So I'm giving the first lecture, and then Tobias is giving the second lecture, which is the important one. But I will try to set up some things for him and also talk about something that is in a slightly different direction. So today I'm going to spend the first half talking about the implementation polynomial, which I promised you, and the second part I'll talk about transverse knots and transverse homology. Okay, so implementation polynomial. So our starting point is going to be, remember we have this thing that I call the knot DGA. We're on knot 3. And this is a differential graded algebra over the ring that I've written there. It's z brackets w plus minus 1, mu plus or minus 1, u plus or minus 1. And we saw yesterday that if we set u equals 1, then at least the degree 0 part of this. So yesterday, last time, so this is the degree 0 part of the CJ. If you restrict to u equals 1, this is the this is what we defined yesterday. It's called the order. Okay, so that has some sort of fairly natural topological interpretation, which again, with this additional u, I don't really know what's going on. Okay. So what I want to do today is to continue considering this degree 0 thing. So the idea is that we're going to consider an augmentation. My augmentation is supposed to go from differential algebra to somewhere, and the somewhere is going to be the complexes. Although I think you can work over other fields as well, but what you see for simplicity. So because this DGA is supported in non-negative degree, this actually turns out to be the same thing as a map from an algebra map from HC0 to C. So in other words, an augmentation from the algebra to Z actually in this case turns out to be the same thing as an algebra map from the degree 0 homology of this DGA to C, and that was an easy exercise because of the exercises. Okay, and correct. Ring homology. And so I'm not going to rehash what the definition of this is, but just think of it as, so from 2 days ago, it's the tensor algebra that's over R that's generated by these degree 0 generators, Aij, so there are n times n minus 1 of those if you have an n braid. And then you run out by a number of relations. So relations, I'll call them polynomial relations, although it's not computed at this moment. In the Aij's and lambda and u. Those are the relations that you get by setting the differentials of the B generators, the C generators, and the D generators equal to 0. Okay. So, now if you have such a thing, so suppose that you have an augmentation like this, this is going to be very bad work. Okay, so there's an inclusion. Okay, so something sits inside of here, and what sits inside of here is the ring itself, R. So R is certainly in degree 0, and its differential by definition is 0, so it sits inside this degree 0 part of the homology. And so what you end up with is if you have an augmentation from the DGA to C, then you end up with a ring homomorphism from R to C. And basically the augmentation variety is an invariant that you get by just considering such maps for all possible augmentations. Maybe I will give it a temporary consideration here, so there's going to be a little bit more so where does this sit? This sits inside of R, C. Okay, so any augmentation you get a map from R to the complexes, and you're just considering the space of all possible maps instead of all possible maps. And because R is that, because R is this, then that's just determined by what lambda, mu, and u get sent to. And lambda, mu, and u get sent to some numbers in the complexes, but they have to be sent in non-zero numbers because there's also their inverses to worry about. So this is actually the same thing as C star cubed. So this is C minus 0. Okay. And the way that you can think about it, given that I rewrote augmentations as something like a map from this quotient thing to C, is essentially you're looking for all possible values of lambda, mu, and u, or all possible ways that you can assign complex numbers to them, so that you can solve all of these simultaneous polynomials in the ARJs. So it's something about you think about the lambda, mu, and u's as coefficients, and you want to choose the coefficients so that the resulting relations in the AIJs has a common solution. So that's what this means. And as such, you can sort of imagine that this thing so that you're solving some number of polynomials for some unknowns, and so what you end up with is some sort of, it should be an algebraic set. So it's not exactly, so you have to take its closure. So this is just, sometimes it'll look like it's a vanishing set for some polynomials, but there might be some points missing or something, and this still doesn't put it in. Okay. Okay, so this is something, it's not exactly clear what this is, but it is at least a non-invariant. And that follows from the invariance of the DGA in some way. It somehow forgets a lot of the information from the DGA, but what I want to convince you of is that it actually retains a lot of information. In fact, we can specialize further, so let's say known examples, I would sort of conjecture that this is true in general. The maximal dimensional part of this variety, so it's a subvariety of C star cubed, is codimension 1, is complex codimension 1. So you have some sort of algebraic set sitting inside of this thing, C star cubed, and the maximum dimensional part in all known cases has codimension 1, and so it cuts out it's cut out by some polynomial. Okay, so definition. In this case, the augmentation polynomial. So this definition actually requires an assumption, which is that this is actually true or not. The augmentation polynomial of K. So I'll write it as aug of K of lambda mu u, and this is a polynomial. You can normalize it so it's actually an honest polynomial of lambda mu and u. Is this polynomial such that the augmentation variety or the max dimensional part? So I'm using completely non-standard notation, but hopefully it's clear what it means. So the maximal dimensional part of this variety is the vanishing set. Of this polynomial. And I should note that it's not, I say the augmentation polynomial, it's not completely well defined, so it's well defined up to units. Actually, if I assumed that it doesn't contain it's not divisible by lambda or mu or u, I guess it's well defined up to, in that case, it's just a plus or minus. Okay. Okay, so let's look at some examples. So here are two examples that I've pulled out on my. So the first one I'm fairly confident about. The second one I just read off of one of my papers a second ago. Is that I use different conventions there. So I think this is correct, but it's not 100% correct necessarily. So these are degree 0 knock-on etymology for the unknot of the trefoil. And for the unknot, you see that, okay, well, if there's going to be an augmentation of this thing, then lambda, mu, and u will have to satisfy this is equal to 0. Right? Because this relation certainly has to be set to 0. So the augmentation polynomial for the unknot, no, I run into problems with my notation, but okay. It's just that polynomial, 1 plus lambda, well, minus 1 plus lambda plus mu minus 1. And the augmentation for the right-handed trefoil, the augmentation polynomial. So how do you get that? So that's the set of lambda, mu, and u such that these two polynomials, when you view them as polynomials in X, have a common root. And you can work out, well in this case it's actually easy just to work out what that condition is. In general, if you had two polynomials in one variable and you wanted to know what condition on the coefficient it is for them to have a common root, you just take their resultant. So this is some sort of well-established algebraic thing, and in the spirit of honesty, I'm actually writing down what this is. Although, I assume it will not be illuminating for anybody. I've copied this from one sheet to another several times. There could be transcription errors, but it's also in the. This one is definitely in the notes, so you can check and see if I made any mistakes. It's also slightly illegible. Okay. Keep that up there. You can stare at that if you like. And what we'll see, or what is sort of claimed by various groups of people, mainly physicists, is that this polynomial actually is a very strong mononomial. So it encodes lots of information, which in sort of decreasing order of commutatively that includes the Humphrey polynomial and some version of Kolonov homology, and maybe SLN, Kolonov-Ruzensky. I'm not even going to write that down because I don't understand how it goes. So I will write down something along those lines in a second. But let me first say, okay, so this is some sort of fairly involved polynomial, and this is something that I've calculated for a fairly large number of knots now. It's very hard to compute in general, but I have computations through a few 10,000 knots, and I'm missing a whole bunch, but anyway. Enough that you can sort of see some patterns start to emerge. So, let's see. So, I should mention this is going to make my life a little bit notationally difficult, but there's a similar story if we first set u equals 1. So this is, if we're going to be in contact with what we did yesterday, you could first set u equals 1 and do all the rest of it. And now what's going to happen is that this will not be, it'll be a subset of not c star cubed, but c star squared, because the u variable has gone away. And what you end up with is a two-variable augmentation polynomial, which I will sort of confusingly write like this. Two-variable augmentation polynomial. So I won't write down the details, but it's exactly what I just did here, except you first set u equals 1, and then that has the effect of cutting down the dimension by 1. And you do that before you take the Zariski closure, before you take the maximal dimensional fraction and so forth. Okay, and why am I bothering to do do this? Well, so first let me say, here's some very basic stuff that we don't know. So here's a couple of things that I believe are true, but we can't prove at this point. Both the two variable and the sort of three variable augmentation polynomials are well defined. Maybe I should say non-zero actually. So the Zariski closure actually is good dimension 1, which was sort of an implicit assumption in defining this thing. And the second one is that you would think that the three variable augmentation polynomial, when you set u equals 1, you get this two variable thing. Because that's like saying you take the augmentation variety, you intersect with u equals 1, and you get the variety that results in this. So that's not completely obvious. So in fact, if you take a three variable polynomial and set u equals 1, you're supposed to get the two variable polynomial. But that's not obvious. There's some issue with dimension counting. So I'll just leave those as conjectures. Okay, so what I want to do is present two relations between these polynomials and things that people already know something about. And by present, I mean probably write down and then refer you to the notes. So, one of them is the A polynomial. And having just done, giving you the definition of the augmentation polynomial, I can say that so the A polynomial is something that's been studied for a while now, and has to do with representations, SL2 representations of the knot complement. And so let me just give you a really quick snapshot of the definition. So suppose that you have a knot and you have a representation of the knot group to SL2C. So if you have such a thing, so there are two distinguished classes sitting inside here. There's the longitude class and the gradient class. And you can then, since they commute, you can simultaneously diagonalize to get rho of the longitude is something that looks like it's up here, and rho of the gradient is something in this form. So lambda here are just complex numbers. So the collection of all, so the all lambda mu in C star squared, where you let rho go over all possible representations, so over all SL to C reps. So that's some subset of C star squared. And just like up here, this is some sort of algebraic subset once you take its Zariski closure or maximal dimensional parts, whatever. Is a zero set of a polynomial in two variables. The A polynomial. Okay, so it's a somewhat similar flavor to the augmentation polynomial, except instead of considering augmentations, you consider SL2C representations. And people know lots of things about this. It's related to hyperbolic structures in the non-complement. It's related to a lot of different things. And so here's a result that relates the two variable A polynomial, augmentation polynomial to the A polynomial. And that says that if you take, so this thing right here, so this is the A polynomial, I need to put in, no I don't need to put in a square. Okay. This is the A polynomial for a knot, and you multiply by b squared minus 1. This divides the augmentation polynomial. The two variable one. Okay.
What's the two variable augmentation polynomial for the unknown?
It is lambda minus 1 times b minus 1. Oops, I forgot to use my square. are actually equal. So that's why I said put in this artificial b squared minus 1 there, so that they'll actually honestly be equal for some lots. So maybe I should say, so not always equal. But they might be equal for two bridge knots, I don't know. I had some idea of how to prove this and never got around to doing it. So for instance, the A polynomial for the 3-4 torus knot is lambda minus 1 times 1 minus in these. So I've taken particular conventions, but okay, so the two-variable augmentation polynomial is this times that times mu squared. So there's a square there, so it's actually supposed to be mu minus 1 now. And there's one more factor which is, okay, so it's not actually this, sorry. So lambda minus 1 times 1 minus lambda squared e to the 12 times mu minus 1 times 1 minus lambda e to the 8. So this is some additional factor. That's not in the A polynomial. And there's actually, in the exercises, I have some sort of guess for where this additional factor comes from. And it's possible that you can actually get all these additional factors from GL-NC representations instead of considering SL2 representations. So I have some sort of way of indicating how that goes in the minutes in one of the exercises. Yes?
Where did SL2 come from? If I take a different specialization of three-variable polynomial, would I suppose it would be seeing higher SLN representations?
Right, so that's a good question. Would we see higher SLN representations? And I don't know. I think maybe not. So I haven't been able to get any sort of similar representation theoretic description for any part of the full augmentation polynomial. But like I said, so if you have a GLN representation with certain properties, then you actually get something in the augmentation polynomial. So that's maybe the most general thing I can say.
So is anything known about other components of the augmentation hierarchy?
For this particular, for the two-variable polynomial, yeah, so this is my claim that at least for the 3-4 and the 3-5 torus knots, the additional factors that you get here are actually gotten from looking at GL3 representations. Did I say something? Okay, this is for those who are curious, but it will not make sense to anyone else. So if you look at, and you look at representations such that of a particular form, so the meridian gets sent to mu, the diagonal matrix which is mu and then the identity, and then the row gets sent to the diagonal matrix that looks like lambda and then anything there. And you look at a set of all possible lambda and mu, then any such thing will sit inside of the augmentation variety. And in particular, anything that's gotten from an SL2 representation, you can easily massage into this form. So this is sort of an alternate proof that the A polynomial invites the augmentation polynomial. I don't know if there's more stuff. I have no idea. These are excellent questions. Okay. Other questions? All right. Actually, because I just said that, I now am not going to tell you anything about the proof. So it's in the exercises also. It's essentially, you use the homotopy theoretic definition for the chord algebra that I gave you yesterday, and it sort of falls right out of that. So the idea is that if you have a representation of this form, then you get an augmentation fairly easily. Okay. Corollary. So this is a corollary that we already saw yesterday. So the point is that for any knot that's not the unknot, the A polynomial is non-trivial. So this is a result of Dunfield and Garofalidis building on work of Kronheimer and Rivka. And from that, you get right away that the chord algebra detects the unknot. And this is something that, again, we saw yesterday already, but this is actually a little bit stronger in the sense that, for the reason that I mentioned yesterday about homology classes or coefficients being able to commute or not I won't say anything more about that. But this is another proof. It's sort of slightly stronger, but technically much more difficult, sort of hidden in the work of HUN-REN. Okay. Oh, and I wanted to make one remark, which is that in the physics literature, at least the last couple of papers that have shown up about this, they make reference to some polynomial that's supposed to be the same thing as a three-variable augmentation polynomial, and they call it the Q-deformed A polynomial. So their Q is our U. So they're thinking of this as a U deformation of the A polynomial. But I sort of just wanted to emphasize that's not exactly correct. So somehow it's not a U deformation of the A polynomial, it's a U deformation at most of the two-variable augmentation polynomials. There's somehow additional components, like this one here, that are an essential part of the story and do not appear in the A polynomial. Anyway, if you see, and Tobias can talk about this, but if you see reference to the Q-deformed A polynomial, just think augmentation polynomial. Right. So this will be sort of the starting point, I think, for some things that Tobias will discuss, is this three-variable augmentation polynomial. So I told you a relation between the two-variable version and the A polynomial. Let me also tell you that, so I claimed, the physicists claim that the three-variable polynomial is supposed to contain all sorts of great information, and I will give you the only thing that I've actually been able to turn into a testable mathematical prediction, and this is something about the Humphrey polynomial. So this is some prediction that comes from physics. And so for some reason it turns out, so let me just say it very quickly and then I'll move on to the transversality. So for all knots k, it turns out that this augmentation polynomial, the three-variable one that I just written there, if you set lambda is equal to 0, which is sort of not quite legal, but it's okay, it's taking some sort of completion of the variety, closure of the variety, something like that. You set lambda is equal to 0 and mu is 1 over u, and u is arbitrary. This is always equal to 0. So this is just a fact. You can actually prove this. Not so unlikely, but anyway. Okay, so what does this say? This says that the point, that the curve 0, 1 over u, u, where u varies, always sits on the augmentation variety. So u. If you look at solutions to this equals 0, so in other words, points on the augmentation variety near this curve, they look like, so to satisfy, well, so lambda is going to be, so essentially I just want to take some sort of Taylor series for this in terms of u. Sorry. So they satisfy mu is equal to 1 over u plus some function of lambda. So when lambda is equal to 0, that's it. But in general, there's going to be some number here, which I'll write as a function of u, plus b over lambda squared. So this is just somehow the information from the tangent space to the augmentation variety at a point on this curve. And all of the information, the first order information is contained in this function right here. Okay, so this looks like I'm stating something, but so far this is all just to define this function f of u. If you take f of u and you just normalize it sort of properly, which in this case is multiplying by u squared over 1 minus u, this is, I think, not such an interesting factor as sort of hanging out. This is in fact supposed to be, so conjecture, this is supposed to be pk of u to the minus 1/2. 0, or pk. Okay, so this is some weird, or maybe not so weird specialization. So z, it depends on whose normalization you're using. So that sometimes people use q's, and then z is q minus q inverse. tells you the specialization of the polynomial. And this is a testable thing, and in fact, in the exercises, one of the exercises is to check this for the HUN-REN and for the trefoil. And you can just do that directly from the, well, now gone, but the augmentation polynomials for the HUN-REN trefoil that I gave you before. And if you know, I guess you also need to know the Helmholtz polynomial for the trefoil, but that's given to you in minutes. And in fact, I've checked this for all of the knots where we've actually been able to calculate the augmentation polynomial, and it's true for all of them. This is a fairly non-trivial check. And I have some idea for how to do this, but I haven't been able to actually get it to work yet. And it wouldn't be very illuminating the way I was thinking of doing it anyway. It's just some sort of push through with some combinatorics. And I don't think it's the right way to do it if it's actually correct, but it would be something. Okay, so the physicists claim more things. They claim that you can get, in fact, the entire Helmholtz polynomial out of this. I say deep physicists like there's like one big group of physicists. So Rafa, let me say Rafa and some collaborators in this thing. They're the ones that have framed this correctly to me, so you can blame them. Okay.
PK of the unknown is 1?
PK of the unknown is 1. Yes, yeah, right. So with that normalization. I think that's, yeah. Okay. So like I said, Tobias will talk more sort of start in this direction in the second talk, but I want to now, with my rapidly finishing time, talk about an application, an actual concrete application of non-finite epistemology, and this is to diverse knots. So any questions about this before I go onwards?
Well, there's no bounds on the degrees of the A polynomial or the augmentation polynomial that you can get without actually computing it.
So right, so the question is, are there Newton bounds on the degrees of these polynomials? Possibly, but not to me. I think there's probably some information you can glean without actually calculating the polynomial, maybe like the degree of the, not the degree, maybe, well, something involving the degree, maybe you can calculate. Actually, somebody who knows more algebra than me should just tell me, what sorts of things can you calculate? If you can't actually calculate this polynomial, because that seems like a difficult business, but I just give you a bunch of polynomial equations and ask, what can you tell me about the set of lambda and mu and mu such that they have a common zero? That would be really interesting to me, but I'm too ignorant.
For example, is there any chance of getting the Morton-Franz-Williams sort of inequalities on the right-hand side, for the thing on the left-hand side?
Is there any chance of getting a Morton-Franz-Williams inequality or improving on this by using this?
Just, I mean, so you have some bounds on the right-hand side,
right.
What that polynomial should look like. And you see those bounds on the left-hand side as well.
Can you see these on the left-hand side? Maybe. I actually had some idea for how to use what I'll talk about next, which is converse to get some bounds on, say, the self-thinking number of the knots, which is essentially Morton-Franz-Williams. I need to think about that again, because that was a couple years ago before all of this stuff. Yeah. Maybe? Great. So let's talk a little bit about transverse knots. And something that I'll call transverse homology. And so let me just give you the one-sentence summary of this, which is, if you have a transverse knot in R3 instead of just a topological knot, then you end up with an additional structure of a filtration on the knot contact homology, which gives you information that's actually an invariant of the transverse knot. And you can use this to get effective invariance of transverse knots. So I think nobody's actually talked about transverse knots yet, right? This is unfortunate. Okay, so I should maybe tell you what they are. So far I've been talking about some sort of context structure on a 5-dimensional manifold. So now I want to actually start with the context structure on R3 itself. So the ambient manifold. And And this is going to be, did I get this right? This is right. So this is standard gravitationally symmetric contact structure, and the knot, so knot T in R3 is transverse, and it's supposed to be oriented if alpha restricted to T is always greater than 0. So in other words, the knot is always transverse to the contact plane, and it's always transverse. It's pointed in the positive co-oriented direction relative to the contact structure. Okay, so it's some sort of interesting question to try to understand transverse knots up to isotopy through transverse knot, which is called transverse isotopy. There's a standard. How much do I actually want to say? Maybe okay, so I'll skip a little bit and just say transverse knots. So this is the content of some classical work of Bentham plus what's called the transverse Markov theorem. So transverse knots up to transverse isotopy. So this is just isotopy through transverse knots. This is actually the same thing as braids of any braid index up to conjugation and positive Markov stabilization or destabilization. So positive stabilization, you take a braid and you replace it by the same braid but with one more strand, and then you put in one crossing there. Okay, so if I allow for negative Markov stabilization also, which is the same thing but with the opposite crossing, then braids modulo conjugation of that is just topological knots. So now I'm restricting what I'm allowed to do to these braids, and this gives me, instead of topological knots, this gives me transverse knots. So to a transverse knot, there are, depending on how you count it, either one or two classical, what are called classical invariants. It's sort of fun to see how the word classical sort of creeps forward. So these were not so classical. Well, self-linking number at some point was not so classical. So one of them is topological knot type. So you can just forget about the fact that the knot is transverse. Just think of it as a topological knot, so that's something. And the other one is the self-linking number, which in this version where I'm talking about braids modulo those things, the self-linking number of a braid is defined to be the algebraic crossing number of the braid, so the right of the braid minus the number of strands in the braid. So this is crossing number, algebraic crossing number, right, braid index. So that's clearly preserved by those two operations there, and in fact it's some sort of numerical invariant. It's an odd integer if the braid is a connected knot. So it's been sort of interesting for a while to try to come up with more invariants that can distinguish more than. So the sort of central question is, if you have two transverse knots and if they're of the same topological type and they have the same self-linking number, is it possible to distinguish them in some way? And sometimes maybe not because they're actually the same. But if they're different, how can you actually tell that they're different? And there are various ways to do this now, and two of them are using some sort of invariant. And one of the invariants is the invariant of non-Floer homology. I think I can now say the invariant. So Ashta, Thurston, and Liska, Ashta, and various other related work by some people in the audience here. So this gives you, so I'll just give you one particular flavor of it. So if T is transverse of topological type K, then what you get out of this is, you go over to this theta hat of T, and this sits inside of it's an element in HFK hat of the mirror of K. And it's a particular migraine that I won't bother you with, but just involves the self-empty number of the transverse knot. But what you're supposed to get out of this is you get a distinguished element sitting inside of the hat version of knot floor homology. There's a similar version for the minus theory. Okay. So I'm just mentioning that in passing. I'll come back to it at the end very quickly. So that's one invariant, and that's been shown to be what's called effective, meaning that you can actually use it to distinguish between transverse knots that have the same topological type and the same self-empty number. Right. So now, what I want to do is I want to give you, so there are two invariants I want to talk about. So that's one of them, which I didn't actually talk about. Okay. So what I'm going to give you is a second effective invariant of transverse knots, and this is transverse homology. So what I'm going to do is just sort of stare at the definition of the knot DGA, which hopefully is on page 6. The definition of the knot DGA. So one thing you might notice if you just look at it, or if you don't look at it and just take my word for it, there are these lambdas, mu's, and u's flying all over the place, but the u's at least only appear ever in positive powers, except for one place, which is the lambda matrix. So if we replace so this is and I studied this one, 30 minutes in this one. 2 by the same thing, but just get rid of the power. So I mentioned when I first described this that the most important thing about this matrix is that there's a lambda in there. The rest of it is just sort of window dressing to make sure that it gives you a topological invariant. So this is not quite going to give you a topological invariant, but it'll be close. So if you replace that by this, so that now the power of 2 is gone, then u only ever appears. So the differential only involves positive powers of u. Okay, u appears all over the place in the differential, but it's all in positive or non-negative powers. So then out of this you can get some sort of, if you do this replacement right here, then instead of getting the knot DGA, I'll get something that is A minus P minus. And this is a DGA over. Now what is it going to be over? It's going to be over R naught brackets U. So let me just remind you, R naught is Z brackets lambda plus minus 1, U plus minus 1. So the point is you don't need to invert U. So you're going to get some DGA with this associated to a braid. So remember, you always start with a braid. In this case, you get something like this. So the theorem is that if to a braid you associate this DGA A minus P minus over R naught brackets U, this is actually descends to an invariant of transverse knots. And its homology, well, let me not say. Okay. So as the DGA is up to stable chain isomorphism, which is this equivalence relation that I didn't actually define, this gives you an invariant of transverse knots. I'm going to give you 0 proofs, but I'm going to think that I'm giving you 2 proofs. So one of them is direct combinatorial check. So because of this this EGA is invariant under conjugation and under positive Markov stabilization. And those are both doable and not terribly illuminating, but also not terribly hard. So you can do that. That's, again, not really the correct proof. I mean, it's the shortest proof, but the correct proof is somehow some geometric proof. And so maybe what I'll do is I want to give you some idea of how this goes, because this explains why you would expect, geometrically this will hopefully explain why you would expect to get an invariant kind of first melt out of this. So where is this, these powers of u, where are they coming from? So here's the really short explanation of how this goes. So the idea is that you apply the conormal construction again. And so remember, suppose that you have a transverse knot T. Well, to any knot, you get the conormal, which now is lambda T sitting inside here, right? That's some sort of torus. But the point is that you can also take the contact structure on R3, and that also lifts to something up in the bigger contact manifold. And what it lifts to is, you know, right, this C color. This is, you can take the conormal lift of the contact structure itself. This actually is just some section of the bundle from ST star R3 to R3, where overending point is just the normalized contact form, normalized so that that's not point. Okay, so the point is that this is sort of a useful strategy in this context where you have a contact structure as well. And then, because if the knot is transverse, then these two things are actually disjoint. That's precisely what it means for the knot to be transverse. So now you can set things up. So you get these things, and then you can then cross them with R, and you get things in the symplectization. So this is a three-dimensional submanifold sitting inside there. If I cross it with R, I now get a four-dimensional submanifold sitting inside of R cross ST star over 3. So this is four-dimensional, this is six-dimensional. You can set things up so that this is actually J holomorphic. Okay, I'm not going to tell you how, but anyway. And once you have that, then this is a four-dimensional holomorphic submanifold. And remember, when we do knot contact homology, we're counting holomorphic disks in the symplectization. So a holomorphic disk and a holomorphic four-manifold inside of a six-manifold should generically intersect in points, and they should intersect positively. Right? So then filter the differential in the knot deviating. So there's sort of this is exactly analogous to how you do this in various other theories. So you have DAI, and remember this was the sum over all this delta and some moduli space, and then k, and maybe there's some power of lambda, and some power of mu. And now, instead of putting in the power of u that I had before, what I can write is u to the intersection of something. And this is the number of points in the intersection of delta and this holomorphic thing. And the point is that because of positivity, this is greater than or equal to 0 because of holomorphicity. And so what this allows you to do is this allows you to associate only non-negative powers of u to the differential, and that's how you get this EGA over this thing where you don't need negative powers of u. Do I use the square root? And this is also why it's a little bit trickier to see what happens if you start with a Legendre knot instead of a transverse knot, because you don't have this. The thing that makes this work is that there's no intersection on the boundary, so this fact that the Legendrian torus and the conormal of the context structure are disjoint is somehow important in this being invariant. Okay, so that was a very, very quick explanation of how this geometric proof is supposed to go. Now let's talk about what this is good for. So here are a few flavors of what I call transverse homology. So transverse homology is the homology of this DGA, but as we sort of noticed before, maybe the homology is not as exciting as actually just the entire DGA itself. You refer to it as homology. So this is some DGA over R0 bracket U. And now you can pass to what people recognize as the hat version of this. Where you set U is equal to 0. And so this is now that U is gone, you just get something over this green R0, which is given up there. Another thing that you could do is you could tensor with R0 brackets U minus 1, and then you do this little thing that isn't so important. You have to reparameterize lambda a little bit to get rid of that. And sort of basically undo what I just did up there. And you end up with a DGA over this. And this is precisely what we've been talking about this whole time. So this is the not DGA. So let me just distinguish parts of this picture. So these things right here, well, everything in the picture is a transverse invariance. But in particular, these two things are, this thing right here, this is what we've been talking about this whole time, and that's weaker. It doesn't quite distinguish between the things. It's actually a topological invariant. Now, we know it's a topological invariant because that's how I defined it. I mean, that's what we've been talking about all this time. But if you didn't know this in advance, and you did this sort of construction from A minus to D minus, you might ask, okay, so why do you get a topological invariant? Well, the point is that, what is this tensoring? So you might think of this as sort of taking the infinity version of this theory here. So what does taking the infinity version actually do? What it does somehow is just forget about the fact that intersections are positive. And once you forget about positivity of intersection, if you're just counting the number of intersections of these two things, that's just telling you something about the homology class of delta. And the homology class of delta, in fact, what exactly it tells you about the homology class of delta is what the class in H2 of S2 is. And the class in H2 of S2 is precisely supposed to be this power of U. So, I won't write it down. Okay, so but there's some good reason why, starting with this minus theory, if you take the infinity version, you should get a topological invariant, and it turns out to be the one we've been studying all along. So it's an invariant. Is it actually good for anything? Well, it would be if I do it at H. So this is an effective transverse invariant. And again, I didn't actually write this down, but effective means that it can distinguish transverse knots that are of the same topological type and the same self-linking number. And how do you actually show this? So what you do is you count. It's something that I mentioned before, which is that I don't really know how to do this in some nice way, but I can do it in some brute force way, which is to count augmentations as Z mod 3. So the point is that everything in sight is combinatorial. You can just have a computer write down the differential and so forth. You can have your computer count augmentations. So you start with a grade, and then you plug this into some computer program which exists on, you put it on the web page, and then you get numerical invariants. This just by counting augmentations over some finite field. So we discussed this I think a couple And so out of a braid, this will give you sort of a whole zoo of numerical invariants. And if two braids give you the same transverse knot, then all of the numerical invariants have to be the same. So often you can just check that the invariants are different for various braids, and that will tell you that the transverse knots will be used. It's not very illuminating, but it is pretty effective. So just to give you some sense of how this does versus other things. So there's some work of top junction mates himself. So he was an undergraduate student of mine and is now a grad student at UCLA. We came up a few years ago with what we call a Legendre knot atlas, which essentially is a conjectured enumeration, basically, of all Legendre knots, in particular knot types. I think it was knot types with arcing as the most 9. And out of this, you can get all sorts of conjectures. So in this particular case, out of the knot types that we sort of conjecturally classified, there are 13 conjecturally transversely non-simple knots. So these are knots with 2 transverse representatives with the same self-linking number. At least 2 representatives. Same self-linking number. And out of these, okay, I'm going to group them into pieces. This is okay, so what I'm drawing now is really not illustrative of anything, but I like pictures. Here you go. So, is that 13? Okay, great. So these 6 represent the ones that are distinguished by the HFK hat invariance in some naive way. So one of the transverse representatives has 0 invariant and the other one has non-zero, something like that. These 10, including those 6, can be distinguished by transverse homology. These 3, it's possible they could be distinguished by transverse homology, but it would be a little bit difficult. I've tried to do it and haven't yet succeeded. There's some sort of subtle difference. It's a subtle thing that you have to distinguish. It's also not necessarily the case that these are the only 6 that are distinguished by HFK hats. And in fact, if you sort of improve your invariant a little bit using naturality, so this builds on work that I'm going to talk about yesterday. But this particular application is something that Dylan and I came up with. 2 more of these you can knock off. By the way, you can also knock off various other things. So you can show that some of the Bierman and Masco transverse knots are distinct, but that's a different talk. So those so far can't be touched by transverse homology, but maybe in the future, I don't know. This last one, I don't know what's going on with that. But it's also possible it could be distinguished by transverse homology, but it's also possible maybe if you take the non-homology invariant and do something to it, you could distinguish. But so the nice thing about transverse homology as opposed to this other invariant is that the HFK hat invariant gives you a distinguished element inside of something, right? So until you do fancier stuff to it, that's just an element inside of the vector space. Transverse homology actually gives you an entire sort of filters theory, which it's much more going to try to extract information from, but in theory there could be a lot more information there. Okay, I'm done. So I'll stop there. Thanks.
Are there questions on this course?
Questions from my course will be directed to me. Yes. Okay.
How does the augmentation polynomial behave under connected sum?
How does the augmentation polynomial behave under connected sum? In some simple way. So it's supposed to behave the same way that the A polynomial does, I think. So I don't have to write this down precisely, but if you set u equals 1, I know what the answer is, which is that if a point lambda comma mu1 is in one augmentation variety, and lambda comma mu2 is in the other one, then lambda comma mu1 times mu2 is in the connected sum variety, and that's a different one. There's a similar statement for the entire augmentation polynomial, but it's a little bit, there's some rescaling going on, so I don't remember it offhand.
More questions? Well, if not, let's thank Debbie again.